Today on the inaugural episode of Fixit Friday, Field Current Regulator board for a Miller 180k. Check it out. Hey guys, so I thought I'd produce some more regular content on my channel, and today what I'm going to introduce is what I'm calling Fixit Friday, where I take something from around the house here and fix it, be it mechanical or electrical. Today I'm going to work on the Field Current Regulator board from a Miller 185k Welder that the chief from Hawaii sent me. So let's dig into this thing and see what we can figure out with it. So what I've got here is the Field Current Regulator board from a Miller 180k. Now this board shows some pretty obvious damage. You can see this diode here, D4 on the board, has actually cracked open. And on the back side, the traces leading to it from the connector to it show some obvious signs of damage there too. You can see actually this one almost looks like some of the lead boiled away or the solder boiled away before the diode finally failed. So what I'm going to do today is I'm going to take this board, I'm going to cut this diode out of there, see if I can find a suitable replacement, and solder it in, and then we're going to go over the other semiconductors on the board and see if we can see any of the other ones that are failed, or if we can at least verify that they don't seem to be. Okay, so I cut this diode out, and you might not be able to read it, but it says P300J on it, which means that this is a 3 amp 600 volt rectifier or diode. Take your pick, whichever is your preference to call it. And I had to look through my part stash, and you know, there's something physically similar, but unfortunately this is a 400 volt 3 amp one. Even though it looks essentially the same size, it's not the same rating. So I'm gonna have to go out and head down to Sale Electronics in Cambridge and get the equivalent. Okay, so happily for me anyways, Miller is kind enough to put the circuit diagrams and not service manuals, but owner's manuals for the 180k Welder on the internet for free download. So I'm assuming that these schematics would fall under the guise of free use and me being able to show them on this video. And we look here, we can see that D4 was the diode that blew. That goes to the connector RC1 pin 12 and is labeled battery in. Now if we go to the circuit diagram for the actual full-on welder, we'll see that pin 12 goes down here to one side of the auto idle switch through a relay and then basically goes straight to the battery. Now as far as I'm concerned, under normal conditions that relay should be closed. It appears to be controlled by the oil pressure, low oil pressure switch. That'll cut power to the unit if it runs out of oil. So, from my point of view, that should almost always be 12 volts, with taking into account the diode drop here. Now, I will admit fully that I don't fully understand how this circuit works. As you can see, D6 and D5 all come to a common point with D4. They both all run through this MOSFET down here, and from there down to ground. So it seems to me the only way that D4 would have blown would be if either D5 or D6 failed and we had an overcurrent condition, or if Q1 turned fully on and humped as much current through it as it could. So I figure anything in that path is worth looking at to see if there's any damage. Now there's also R14, I believe it is, and D2, but they're going through a capacitor, and once the capacitor charged, it would stop passing current anyways, so it doesn't seem likely that that was the source for the high current condition. So what I feel I should really test, I should test all of those diodes, D6, D5, we'll test D2 for the sake of it, and I don't have any way of testing the MOSFET, unfortunately, with Q1 labeled Q1 on here. So in any case, we'll test those, see if they work correctly, and we might test a few of the other components that we can. Once I get a replacement for D4, we should be able to apply some power to this circuit and see if what is it called? The regulating pulse current or pulse width modulator that controls the MOSFET. See if that was damaged, or we can see if the op amp was damaged by any sort of a surge. There's a few other diodes in the circuit we can test, but that's most of the semiconductors in the circuit. So let me set up and we will have a look at these other diodes and just do a quick test on them. Okay, so I've got my meter set to diode or continuity mode, and all that means is that for continuity mode it beeps if there's a low resistance path here. But I don't expect to see that beep. There's going to be some internal resistance in the diode, and I don't know if this multimeter has enough voltage to do anything more than just bias the diode. Nevertheless, I've got the board here with a connector that I salvaged from an old PC power supply and cut it down a bit so that I'd have a little bit easier way to test it. Now, if we look at the circuit diagram for the field current regulator, we'll see that we want to test D5, so it goes from pin 11 on RC1 through to that common point that we can see on the board here where the other diode burned off. So from the direction that it's showing there, if we go from this terminal, which is pin 11 on that connector, to here, we should see a relatively low resistance. Not necessarily zero, but some, certainly not infinite resistance. And we're seeing, according to this thing, it's reading like 1/2 a K, which I don't think is accurate. I don't think that diode test mode is meant to be an accurate resistance test range. It's just something for testing diodes and checking continuity. So now if we reverse these terminals, we shouldn't see any, we should see infinite resistance. So the meter shouldn't react, and as we see there, we're not getting anything no matter where I try and probe around here. So that diode looks good to me. So next one we're going to test is, we might as well test D2. Okay guys, I'll interrupt myself and say I'm editing this and it's really long. I'll skip most of the rest of the diode testing. I think you get the idea. Put your meter on diode test mode, put the black lead on the banded side of the diode and the red lead on the other side. In that direction you should see the meter react. Then reversing the leads, red on the banded side and black on the other side, you should see no current flow indicated on the meter. So from this point you can take it as given. I've tested all of the rest of the diodes that I could and all checked out. Note, I didn't test SR1, the full wave bridge rectifier, but it seemed very unlikely to be damaged, and spoiler, later on it was obviously working. There were some exceptions. Diode D2 has resistor R14 in parallel, so you don't get a useful measurement out of it, since current will always flow through R14. As well, D1 cannot be tested on, as R15, R16, and R17 provide another path for the current flow. And once again, the same is true of D3 and R13. I'll also note that D3 is a Zener diode and is meant to break down at a calibrated voltage, and certainly my meter can't test that anyways. I think I'm safe in saying that D1, D2, and D3 aren't likely to be damaged, so I'm safe in ignoring them. Back to the video. So about the only remaining test that we can make on this board is to check that the MOSFET is okay, or that the MOSFET is not shorted. So what we'll do is we'll probe the location basically between common and the outputs of D4, D5, and D6, which was that common location here. Now D4 is obviously burned off of here, but from here, this goes to the MOSFET, and there's the other terminal of the MOSFET, which is common, which is pin 5 of RC1. So we should not see any current flow through that MOSFET, at least in this direction. So if we check that out, the meter's not on, turn the meter on, and we check that, and we're seeing pretty much zero resistance, which is very bad. That probably means that the MOSFET is blown. We'll check the other direction here, not that we really need to because it shouldn't have been conducting in that direction, but we check this direction as well, and we see 0 resistance here as well. So it looks like the problem that caused D4 to blow was probably the MOSFET. You know, too much current was run through it, and it blew and short-circuited, closed, or short-circuited, and that caused too much current to flow through D4, which is connected to the battery of the generator, and blew up D4. So we have two thick components that we're going to have to replace on this board, D4 and Q1 MOSFET. Now I know for a fact they don't have any MOSFETs like that one, so I'm going to have to pop this one off the board and see if I can figure out what a part number is for it. So I'll desolder that, take it off the board, and we'll identify it, and I'll bring you guys back. Okay, so I removed the MOSFET from the board, and in case there's any doubt that it was the short-circuited, measure across the drain and source. We're seeing 0 ohms there, and in the other direction we're also going to see 0 ohms. Oops, let's see if we can get it stable. 0 ohms. So the MOSFET is shorted. So what seems to have happened was the MOSFET failed for whatever reason it failed, whether or not it was because the machine was being overloaded or not, I don't know. But the MOSFET failed. It failed in a way that it was short-circuited. The D4, diode D4, was basically directly connected to the battery, and since D4 and the MOSFET provided a direct path to ground for the entire power of the battery, it basically would have flowed, you know, however much current the wires in the battery could have delivered through the MOSFET and D4 until D4 finally failed. So I'm going to have to scrape the conformal coating off of D4 so that I can identify, or sorry, off of Q1, which is this MOSFET, so that I can identify it, and I will go down to sale and pick up both. And hopefully that's the only problem. Now the problem with the MOSFET failing is there's no guarantee that it didn't kill the regulating pulse width modulator, the control circuit for the MOSFET, but I'm going to hope not, and if not, I'm probably not going to be able to get that at sale anyways. I'd have to order it online. So we'll assume that's okay. We'll replace the MOSFET in D4, and we'll go from there, and I'll do what testing I can locally. Anyways, guys, a few more minutes and from your point of view, but a couple of days from my point of view, and I'll have the parts and I will replace them, and we'll see how we go here. Hey guys, so it's been about a week and a half, and I'm back here, and went to sale and found an exact replacement for the original diode there. This is 1N5406, 3 amps, 600 volts, so it's the exact same rating, looks to be exactly the same size. Not that that matters, it's a rating I was more concerned about. As well, I got what I'm going to hope is going to be an adequate replacement for the original MOSFET. Now the original MOSFET was this one, which was an IRFP350. What I picked up was an IRFP450. The difference in the specs is slight, but you know, I'm hoping it's not significant. This one was, I believe, a 400 volt 11 amp device, the original device. The new device is a 500 volt 14 amp device, which, you know, obviously it's better in every way in terms of its rating, but it also has slightly higher internal resistance when it's fully on. The original was 0.3 ohms, and the new one is 0.4 ohms. So it's like about a 33% increase. It shouldn't be significant. I figured out at you know, full current, it's just over a volt of drop across the device. It does mean it'll dissipate a little bit more power, but I don't think it'll be a big deal. And by that I mean it's going to generate more internal heat because there's a higher voltage drop across the device. In any case, it's the exact same package, so it's good. As well, I found that the original chip there as this one, the regulating pulse width modulator. And it's actually in a slightly different package. It looks to be a ceramic package as opposed to the plastic package of the original. I don't know if that means it's mil-spec or not. In any case, I'm not going to replace that unless I absolutely have to, unless it's obvious that it's not working. Even if I'm not sure if it's working, I'm not going to replace it. You know, I'd rather risk having the chief send it back to me than, you know, to replace that one chip than take a chance on breaking things, you know, worse by replacing something that didn't need to be done. So I'll just quickly go over my theory on what caused this to fail. I believe this device overheated, and that's what caused it to short. Now, whether or not it was being overdriven or not, I don't know. You know, it's probably unlikely it actually was. But what I think the problem was is if you look at the back side of this device and you look at the heatsink, there's not a lot of the heatsink compound. Like, there's none visible on the device itself, and there's only a little bit on the heatsink. And if you actually notice on the back of the device, you can actually see some of that yellow conformal coating actually got underneath the device and was actually probably insulating it thermally from the heatsink itself. Not to mention the fact this heatsink is so gooped with that conformal coating that may actually affect the heatsink's ability to work correctly. Nevertheless, I've got some proper heatsink compound here that I'll use between the new device and the heatsink, and I'll clean the heatsink off first before I solder anything on. Then we should be good to go, and we'll give it a try with a quick test there after that. Okay, so I've installed the components. You can see the MOSFET, good amount of heatsink compound behind there, but not too much. I squeezed it all out by pressing the MOSFET hard against the heatsink, so it's only going to be a very thin layer, so it has the best conductivity it can have. As well, I've put the diode in, and in the correct orientation, and they're all soldered in. Here, the trace had been burned off. You can actually see how it turned black at one point when the other diode failed. So that's soldered directly to the terminal of the connector. And I've already checked that with the continuity tester, and it works correctly. You can see this big caterpillar of solder here. That's actually burying the lead for the diode. So we got the best conductivity we can have there. I've soldered the MOSFET in. It's all ready to go there. So what I'm going to try right now is we'll go to the circuit diagram for the field current regulator, and I see that pins 3 and 4 of RC1 have 18 volts AC coming in. And if we look at the circuit diagram, we can see it goes through a rectifier, has a capacitor on it. It's the most basic regulator you can have, and a current limiting resistor in series with that as well. And that applies power to the regulating pulse width modulator, and that in turn has a plus 5 volt reference that is being used to power the op amp. And about all I can check right now is I can apply that 18 volts AC to the board and see if the field current or regulating pulse width modulator is giving us the correct reference voltage. And if it is, I think we'll be good. I can also see if the output, you know, like is in a reasonable range. Like the input of the MOSFET is supposed to be around 10 volts to be fully on. So if I see it oscillating between 0 and 10 volts, then that's what I would pretty much expect for the pulse width modulator. Apart from that, there isn't going to be much more I'm going to check. So let's go and wire this thing up. It's going to be a bit of a faff because I'm going to have to go and connect my Variac to an old transformer out of an old modem from the mid-80s and regulate out the plus 18 volts. But in any case, we can give it a go, try it out, and see if we see any smoke. Okay guys, I finally have my test rig all set up and tested it and working. I'm happy to say that as far as I can tell, the board is working. But I'll show you the rig because it's got to be amusing. So, I've got a oh wow, come on, there we go. I've got a Variac here, coupled to a transformer, that's supplying power to the board through here. Now that's supplying 18 volts AC. This is a 24 volt AC transformer, so that's why I'm using the Variac to dial down the voltage a bit. So I don't think that this board is likely to be that sensitive, but you know, why would you push it? And what I've got here is I got my little portable oscilloscope. I've got one drill battery that provides the current sense, or actually it's weld sense signal line. So you can hear it engaging the relay that clicks over the weld sense line. I've got another battery that's simulating my voltage supply for the field coil, and for the field coil I've got a wiper motor. I tried a few different things. I tried some LED fog lights. They didn't have enough of a load. I tried a proper fog light for a tractor. That didn't have enough load. So I dug around and I found this thing and wired it up, and I'm pretty happy to say that it seems to be working. Also have my brand new meter. I've seen it earlier in the video there. Replace the e-meter I was using earlier in the video because this is a much nicer meter, and just as a nice coincidence, pretty much as soon as this meter arrived, the other meter just up and died, completely failed. So anyways, so what I'm going to do is I've got this oscilloscope monitoring the gate of the MOSFET. I just was checking to see if it was hot because I had been running it earlier. It's monitoring the gate of the MOSFET, and what you'll be able to see is you'll be able to see the pulse width modulation as well. I've got this potentiometer to control the reference voltage of it, which would be like the dial on your unit to control the welding current. So I'm going to put this thing back up on its stand here. I'll probably just zoom in on the oscilloscope. I don't know how well it's going to show up, but we'll see, and we'll see how we go. Now, hopefully the oscilloscope isn't about to die because I dug this thing out, hadn't used it for probably a year. The battery was down quite badly. Okay, let me pause you guys and I'll come bring you right back. Okay, there you are, centered on the oscilloscope. I think you're going to be able to hear when the motor is working. The field coil on the welder generator there seems to need at least a minimal amount of current going through it at a time. It looks like it's meant that when it doesn't sense welding, it pretty much punches the current to the field coil. Not sure why. I'm assuming it's because you want a good hit when the thing first starts out. One of the things, I forgot to mention this, but I'm not going to worry, but I'll just mention it to you. I did check, obviously, the regulating pulse width modulator, the mouthful there, and it is outputting 5 volts, which is what I expected. That was part of what the testing that led up to this point, which is why I went and I bothered to here, sorry, I'm just plugging that in, if it'll stay in. Part of the things I tested, kind of off screen here, because the video's been getting a little bit too long and I didn't want to make it too insane here. Anyways, so that all that appears to be working, and I will now do my demonstration of it operating. Now, as I said, it seems that the field coil needs a minimum amount of current running through it before it, it's kind of idle. And like I said, I think it's for that. So what I'm going to do is I'm actually going to engage the, well, actually I won't. So what happens at first is this is with no welding sense, welding current sense line active. And basically what it does is there's almost no pulse width modulation. Here, I'll change the units per division. There we go, 500 microseconds per division. So you can see a couple of different pulses on the line there. Now we'll engage welding sense, and now it's using the reference from the potentiometer to control how fast it's going. You can see it's all over the place, probably because it's not a particularly good load, but nonetheless you can see it pulse width modulating, and I can actually turn it down now. Right now we're running about 1.3 amps through that. down to about 1 point. Okay, we dropped right off to about nothing. We'll crank it back up. Yeah, it's a little bit of a bad load because it needs so much startup current to start moving. We're running it right now at about 1.2 amps, and you can see that it's all over the place. If I ramp this thing all the way up, we'll see. Actually, I went the wrong way. We'll see that it almost completely stops pulse width modulating, and it's running about 1.6 amps through that motor. And we can turn it down a bit. Yeah, it doesn't. The motor's difference between, you know, running at full speed and slowing down dramatically is only about 0.3 of an amp. It's at 1.3 amps. It was 1.6 at peak. So, and as it drops off, you can slow it down. So I'm pretty satisfied with the fact that I think this board is working. See, like when the motor stalls, the current dramatically drops off in it. So it takes a fair bit more to get it going again. So you can see right there, it's not actually trying to do much voltage regulation, but as I turn the potentiometer, you can see, yeah, the width increased a bit. It doesn't seem linear. I don't know why. But it may be there is such a thing as a logarithmic potentiometer, and maybe that's what's supposed to be in there. What I'm using is a multi-turn potentiometer. In any case, I think I'm satisfied that this works. So I'm going to shut it all down and say thanks for watching, guys, and come back in about 2 weeks for the next Fixit Friday. Thanks for watching. Don't forget to rate, comment, and subscribe, and check out the affiliate links in the description.